All right, kids, we're back. Welcome to Chemical Reactions. This is the beginning of the notes. We're going to get through numbers 1 to 26. I got a really cool explosion to do in a little bit. I'm going to have to get up and shut the lights, and you still should be able to see it pretty well. Okay, chemical reactions. In a chemical reaction, bonds get broken or bonds get formed, and sometimes both happen. In every single chemical reaction, whatever you're starting with, you end up with something different. Okay? New substances will form, and those new substances have new properties that are unlike the properties of the reactants. Now, we're going to learn about 5 kinds of chemical reactions in the next week or so, week and a half. And there's about 14 that you have to know by the end of the year. But the first 5 are the most basic ones. And this very first one is called synthesis reaction. And in synthesis, small things combine into larger things. Sometimes it's called a combination reaction. I don't really like that name, but occasionally that's on the regions, but it's the same thing. Synthesis reaction, we're going to synthesize bigger things from smaller reactants. So here we go. In a synthesis reaction, smaller reactants combine to form larger products. In the abstract, not talking about real chemical symbols here, but in the abstract, A plus B equals AB. In a sense, the blue reactants, A and B, combine and form something new called a product, which is AB. Now, these are just letters. This is like X, Y, and Z. These letters don't really mean anything. That B is not boron, and there's no elements with A. The abstract literally means in the abstract. You could use this and that becomes something else. But A plus B equals AB. And you need to be able to come up with an abstract for each of the 5 chemical reactions. You'll also need to be able to come up later on with examples. And you'll get good at this. This is the first day. Here we go. Reactants are the stuff you start with, right? They react together and they form into the products. The products is what you end up with. So we have reactants at the beginning and products at the end. In a synthesis reaction, there's 2 or more reactants and they form into at least one larger product. Now, sometimes you have a bunch of reactants and a bunch of products, but if one product is larger than the others, we generally call that a synthesis reaction. Now, energy is required to start all chemical reactions. All chemical reactions need to start. Just because stuff comes together doesn't mean it's going to react. Sometimes if you put things together, they do react because the room temperature energy or the temperature of the reactants themselves is enough to get it started. But sometimes, like the reaction today, in the back of the room, can you see it? There's a blue balloon hanging out there. Balloon filled with hydrogen, just like the one from the first day. That balloon's been hanging out all day. Nothing's happening. That's because in order for it to react and explode, it needs enough energy to get started. And the room is not hot enough. If it was in a really, really hot room, I'd probably even hotter than the room could get. But if you heated it up enough, it'd explode. It would have enough energy to react. Now, if a reaction releases more energy than it takes in, like it's going to take some energy to start it, but if it gives back more energy than it took to start, we call that exothermic. More energy is on the product side. But some reactions, and we'll see some of them later on, not today, if it takes more energy to get started, but then the beaker or wherever that reaction's happening gets colder, it's absorbing energy. That's called endothermic. So we have exothermic and endo. Exo is to the outside. Endo is to be absorbed inward into the bonds. So in an exothermic reaction, the immediate area of the chemical reaction gets hotter because energy is released, generally as heat. Now, on the very first day, I blew up a balloon of hydrogen gas, not helium. Helium doesn't react at all. And it turned into a fireball, which I joke because, do you remember this song from Pitbull? It's already, this song is getting so old. At one time, this was a cutting edge slide. Pitbull used to sing a song, I think it was called Fireball, but he used to say it like that, Fireball. we're going to explode this. And we don't have to protect our ears. I have to protect my ears, but you're not here. You're at the Zoom. Now, before we do this, we got to be able to write a few things. We're going to write the word equation, which is going to describe in words what's going on. And then we got to write the chemical equation. We're going to actually balance the chemical equation soon. Now, the word equation, for what we're going to do, we're going to combine the hydrogen, which is an element, with oxygen in the air. Now, the air has got a lot of gases. The air is only about 18% oxygen, maybe 19. Most of the air is nitrogen and actually doesn't react very much at all. Pretty stable and doesn't like to react much at all. There's carbon dioxide, there's probably some methane, there's probably some helium, there's probably some hydrogen, there's H2O gas, H2O vapor. But the word equation for the chemical reaction, what's actually going to react here, it's going to be hydrogen and oxygen gases form into water. Or you could say it a different way. Hydrogen and oxygen gas form dihydrogen monoxide. You can sound smarter if you say it that way. Or you could say hydrogen and oxygen gases synthesize into water. It's very important here when you write a word equation. There's no right way, but you want to be simple. You don't want to be too elaborate with a lot of words, and you don't want to say it backwards. You don't want to say water forms from hydrogen and oxygen gas. No, so talk in a straight line. Try not to talk with my accent, but talk in a straight line. The reactants become the products. That's it. Now, if you want to elaborate, you could say form or synthesize. Synthesize is a nice word. They combine. You could say combine. There's many ways to say it. But you want to be clear, concise, and don't say it backwards, right? You could say water forms from hydrogen and oxygen gas, but it's a pain in the neck because you start writing and all of a sudden you got to erase everything and put it back in the correct order. All right. To write a balanced chemical equation, the very first thing we have to write is called the skeleton. We got to kind of lay out the bones. And in order to do that, we have to write the proper formula. So we're going to use this red skeleton, this word equation to write the skeleton. Hydrogen and oxygen gases make water. For number 12, we have to write the chemical symbols. Now, the symbol for hydrogen on the periodic table is H, but to write the formula, hydrogen is a Hunkelbrief twin. It's a diatomic element. It doesn't exist as single atoms. It exists as two at a time. So the formula for hydrogen is H2. And then and is a plus sign. H2 plus oxygen. Now oxygen, remember, two holes in your nose because oxygen's diatomic also. H2 plus O2 make or forms. That's arrow. H2 and O2 arrow. And what's the formula for water? You knew that. H2O. The plus sign means the reactants combine and they react together. The arrow means they turn into. It's kind of like an equal sign. This equals that. You don't write the dashes in. I have these dashes here so that we can balance the equation soon. And then note this blue stuff. G, G, G. G stands for gas. Sometimes it could be L for liquid. Sometimes it could be S for solid, solid liquid gas. There's also one other phase that we have in our class, like when a salt dissolves in water. When something dissolves in water, it's not a liquid. Salt can be a liquid, but it's got to be thousands of degrees, super, super hot. You can melt it into a liquid. But if you dissolve something like salt into water, it becomes AQ, aqueous. We don't have any aqueous here. The hydrogen's a gas, it's in the blue balloon. The oxygen's a gas, it's in the air. And we're going to make H2O. But we're going to make it in a very, very hot explosion. So there's probably not going to be any H2OL for liquid. It's all going to be so hot, it's going to jump into the gas phase. And actually, we're not going to see the water, which is too bad. We're going to see the exothermic part, but we're not going to see the water. Now, this is not balanced. There's two hydrogens on the reactant side, and there's actually two hydrogens in water. But look what we got going on here. Oxygen is diatomic, O2, as a reactant, but there's only one O in water. We seem to have lost an O. You're not allowed to lose anything in chemistry. Matter cannot be created or destroyed in a chemical equation. So we got to deal with that. Now, we're going to have to rewrite that. Now, this is Glinda the Good Witch from The Wizard of Oz. And the best line in the whole movie is when she says, it's always best to start at the beginning. How do you balance a chemical reaction? Now, honestly, in person, this is better because I can write on the board and I can erase. So try not to write anything yet. And if you write on the dashes, which is okay, I guess, to use a pencil and erase, or write small because you're probably going to cross it out and fix it. And that's okay. But you have to talk yourself through this. You have to say what I say. Say it to yourself. I can't hear you. You're not going to embarrass yourself. Nobody in the class can hear you either. But you say it with me. Here we go. From the beginning, I got two H's on the reactant side, and I got two H's on the product side. So far, so good. You can see that. So far, so good. Now, I have two oxygens on the reactant side in O2, but there's only one oxygen on the product side. That's a mistake. That's bad. 2 and 1 doesn't work. So what are we going to do? Now, if you were here and I was writing on a board, I would just make it H2O2 and say, oh, look, 2 hydrogens and 2 oxygens. Perfect, except H2O2 is not water. H2O2 is an ionic compound called hydrogen peroxide, and we can't make that. We want to make water. The skeleton is written correctly. Hydrogen is diatomic. Oxygen is diatomic. And water is in a 2-to-1 ratio. And it's not balanced. And that's a problem, and we're going to work that out. Now, the only way to fix this, because we can't change H2, we can't change O2, and we can't change H2O. But what we can do is say, wait a second, if I have to have 2 oxygens in the product, I'll put a 2 in front of the water, and I won't make 1 H2O, I'll make 2 H2Os. Now, I don't know what the next slide's going to say. No, I put the 2 in front of the water, but that would give me 2 H2Os, which means 2 H2s, 4 hydrogens. And if there's only H2 in the front with 2 hydrogens in the reactant and 4, the only way to make that work is to put a 2 in the front of the hydrogens. So now I have 4 atoms of hydrogen in the reactant, and I have 4 atoms of hydrogen in the product. I have 2 oxygens in the reactant side, and I also have 2 oxygens in the product. There are the same number of atoms, the same number of H's on the front and the back, the reactant and product, and there's the same number of oxygens in the reactant and the product. This is called being balanced, but it's not in a 1-to-1-to-1 ratio. It's actually in a 2-to-1-to-2 ratio. We don't have a number 1 in front of oxygen, but there's only 1 O2. So the ratio is 2 hydrogens to 1 oxygen makes 2 waters. And what you see here is, in this balanced chemical equation, you can't make just 1 water. The only way to make 1 water is to have 1 molecule of H2 and a single atom of oxygen, which is very hard to come by because the oxygen's so reactive and unstable by itself, it doesn't even exist that way normally. The only way to make this is to take 2 hydrogen molecules with 1 oxygen molecule and make 2 waters. Now, this is kind of like Legos. You take the H's and the O's apart and you put them back together in a different shape, but you have the same number of H's and the same number of O's. Now, I talk too much, right? So I'm going to go in the back. I got to turn on the fire. I'm going to turn off the lights, and I'm going to blow up this freaking balloon, and we're going to see synthesis. So you hang in there, all right? You keep watching. I'm making progress. I hope you can see me. So I'm going to move you. We're on the go, kids. Oh, maybe I'll go this way. I'll put you on the other side so you get a better view. You see that balloon? Good. See this? I got a Bunsen burner going. When a Bunsen burner is burning, when the methane is burning, that's not a synthesis reaction. It's called combustion. That's the fifth reaction. We'll get to that. Now, I'm going to use that Bunsen burner because I don't have a little clicker lighter today, and I'm going to light a candle on fire. The candle is taped to a meter stick because I don't want to get too close to this balloon because it's going to explode. Now, the candle is going to combust also. It burns. It's a different chemical reaction. We won't learn about that till after Thanksgiving. But when the candle explodes the balloon, it's going to look like it's on fire because it is. And it looks like it's burning, but it's not burning. It's just synthesizing super fast, and it's very exothermic. So here we go. So I got the candle lit, and this is going to be synthesis. How cool was that? And see what I have here? See this little piece of balloon? You know what this piece of balloon is called? It's a smithereen. I blew that balloon into smithereens. Holy cow. That was fun. I got a great job, you know. I'm a chemistry teacher. Let me go turn the lights on. I'm back. Okay. That reaction was very exothermic. We started out with a whole lot of molecules of hydrogen, and it takes two of them to react with every molecule of oxygen in the air. We didn't use all the oxygen in the air. I wouldn't be able to breathe. But for every 2 molecules of hydrogen, 1 molecule of oxygen was used up and combined to form 2 waters, and a lot of energy came out. That was that fireball. Now, energy went in, right? I had to use the candle to get it started, but a lot more energy came out. So net, overall, way more energy came out than went in. This is called exothermic. Now, this is an important line, number 18. When the bonds form, energy is released. When hydrogen and oxygen bond together, when a bond forms, it's so stable that all the anxiety, all the stress is released, and it comes out usually as heat and explosion. So in this case, it takes some energy to break the bonds, a little bit from the fire, and then as the reaction goes forward, more energy is used up to break the bonds, to open the hydrogens up, and to open the oxygens up. But when the hydrogens and oxygens bond into water, that makes it super stable, so all the energy that was in that system is released as heat. Now, 18 is what you have to memorize. When bonds form, energy is released. The opposite's also true. To break bonds, energy must be absorbed. In order to start this reaction, I had to insert energy, and that energy opened up the oxygens and opened up the hydrogens, which allowed them to have that potential to bond. And if that potential exists and they do bond, the bonding releases so much more energy that it comes out as a huge explosion, like a fireball, like Pitbull told us. Now, in the black in the front here, number 20, energy is required to break open the bonds that hold hydrogens together and oxygens together. To break bonds, energy is absorbed. The energy goes in and it breaks the bonds open. But when the water forms, the water becomes super duper stable and a lot more energy is released. So net exothermic, when bonds form, energy is released. To start it, you need energy to start breaking the bonds. Then a lot of energy is released. Some of it keeps breaking bonds, and then much of it is released when the bonds form again in water. Now, we're going to write some equations. We're going to try to balance chemical equations. We're going to add phase symbols as we can. Number 22, sodium is a metal. Chlorine, together, sodium and chlorine are going to make table salt, sodium chloride. So we have to, a word equation, sodium and chlorine yields sodium chloride. You could say it a lot of ways, right? Sodium and chlorine synthesize into sodium chloride, or sodium and chlorine form sodium chloride. From this word equation, we're going to write the chemical symbols. The formula for sodium is number 11, Na, and it's a metal, so it's a solid at room temperature, solid in this experiment. NaS. Chlorine, think. Hunkelbrief, Cl. Chlorine is Cl2, and the skeleton is going to look like this. Na plus Cl2 yields NaCl. Now the phase symbols, sodium's a solid, chlorine is a gas. You might not know that, but I'm telling you. Sodium chloride is that white crystal that's in your kitchen. It's a solid. It's always a solid for you, right? Unless you dissolve it in water, it's aqueous. Now, to balance this, say to yourself, I got one sodium in the front, I got one sodium in the product, so far so good. But I got two chlorines and one chlorine, and that's not good. 2 and 1. So let's go through this nice and slow. One sodium, two chlorines. How am I going to get two chlorines in the product? Can I make it NaCl2? No, I cannot. The formula is NaCl. Once I write it correctly in the skeleton, I can't change the formula. I'm not going to be able to make just one sodium chloride. Look what I had to do. Two sodiums. I need to do that. Let me see how do I do this correctly to explain it. In person is a little easier. Doing this in slides. Since there's two chlorines in the reactant, I had to put that 2 in the front of NaCl. But if I do that, I have two sodiums. I need to have two sodiums in the reactant as well. In this balanced chemical equation, we have two NAs in the reactant, and I have two NAs in the product. I have one molecule, Cl2 chlorine, in the reactant, and I have two Cls in the product. So this is now a balanced chemical equation, and it's in a 2 atoms to 1 molecule to 2 formula unit balanced chemical equation, a 2 to 1 to 2. Now we don't write the 1 in front of chlorine, Cl2, there's one Cl2. So it's in a 2 to 1 to 2 ratio, simple whole number ratio. John Dalton loves this. I love it too. All right, iron and oxygen are going to synthesize into iron Roman numeral 3 oxide. Iron is a metal, oxygen's a gas, and iron number 3, iron Roman numeral 3 oxide, that's called rust. Rust is a solid also. So we're going to write the formula for the skeleton, phase symbols, right? Fe solid plus O2 gas, arrow. And what is this? Iron Roman numeral 3 oxide. You got to do this. Iron's a positive 3 ion. Oxygen makes a negative 2. Crisscross. It's going to be Fe2O3. Iron is a solid. Oxygen is a gas. And then rust. You know what? I think I'm going to use this pen, and I'm going to try to write here and see if we can't help you do this. Now, this is how we're going to start. There's one iron in the reactant. There's 2 irons in the product. So first, I'm going to put a 2 here. Oh, that's no good. Let me undo that. And how do I write? I don't draw enough. Draw. Here we go. I'm going to make this a 2. And don't be copying this yet. Do some thinking. Put your pens down. So now I have 2 reactants in the front, and I have 2 reactants in the product. So far, so good. Now, there's 2 oxygens here, but there's 3 oxygens back here. 2 and 3. 2 and 3 are different. I got to give you a little heads up on how to balance a chemical equation. There's a lot of ways to do this, but think about this. 2 and 3 are even and odd. If I double the even one, this is still odd. No matter what you do to the even one, it's always going to be even, and the odd one's always going to be odd. So the rule of thumb is whatever the odd one is, in this case 03, let's double that. So that means I'm going to put a 2 right here. And by doing that, I now have 2 O3s, which gives me 6 oxygens, which is an even number, and I can deal with that. How am I going to get 6 oxygens over here? How am I going to get 6 O's? Because I have 2 O3s. That's 6 oxygens in the product. How am I going to get 6 oxygens in the reactant? Well, I got to put a 3 here, right? Let's start over to make sense, see if we got this right. So I have 2 ions in the front. How many ions do I have right here? Uh-oh. We had 2. We had 2 in the product, but now we have 4. How am I going to get 4 ions in the reactant side? Could I make this Fe little 2? Nope. I actually have to cross this out. This has to be a 4. I need 4 ions on the reactant side because I have 4 ions here in the product, 2 Fe2s. And then I have 6 oxygens, and I have 2 O3s. 2 times 3 is 6 oxygen. Now it's balanced. It's in a 4 to 3 to 2. Let me get rid of this pen. 4 to 3 to 2 ratio. It takes 4 iron atoms plus 3 oxygen molecules to make 2 rusts, because rust is Fe2O3, Fe2O3. We have 4 irons. Here we have 2 times 2 irons. That's 4. Then we have 3 times 2 oxygens, which is 6. Here we have 2 times 3, which is also 6. Listen, balancing equations is tricky business. Let's try another one. Aluminum and sulfur are going to synthesize into aluminum sulfide. Aluminum is Al. It's a metal, Al with a little s. Sulfur is just a nonmetal, S, also a solid. You might not know that, but it's a solid. So aluminum plus sulfur, Al solid plus S solid turn into. Now, aluminum makes a positive 3 ion. Sulfur only makes a negative 2 ion. So the formula for aluminum sulfide is Al2S3. Now here's one more thing you got to keep in your head. This will help your life. Ionic compounds in our life are always solid unless you dissolve them in water. They're never going to be liquid and never going to be gas because they have super high melting points and crazy high boiling points. So ionic compounds always come up solid unless you dissolve them in water. And there's no water here, so we're not doing it aqueous. So the skeleton is going to be aluminum solid plus sulfur gas. That's a mistake. It's sulfur solid, right? I don't know how that came up. Who made this slideshow? Ye gads. Sulfur solid. I'll fix that right now because I don't even like looking at that. It's a solid. There we go. Makes aluminum sulfide ionic solid. So in the front, there's 1 aluminum. We need to have 2. So the first thing I'm going to do to draw, I'm going to get my pen to draw this a little. Draw. I'm going to have to put a 2 here because there's 2 aluminums and there's 2 here. Now for sulfur, I have 1 sulfur right now. I need 3 in the back. So I have to put a 3 here. 2 aluminums in the reactant, 2 aluminums in the product. 3 sulfurs in the reactant, 3 sulfurs in the product. What number goes right here? Well, you could put a 1. It's in a 2 to 3 to 1 ratio, but you know what? We don't write 1s. We are number 1 in chemistry. We don't like to write 1s. Let's see. How am I going to get rid of this? Clear all drawings. X out. And now, look at that. Oh, we got to fix that. It's a solid. Who made this slideshow? 2 aluminums and 3 sulfurs make 1 aluminum sulfide, 2 to 3 to 1 ratio. Here we go. Potassium and bromine make potassium bromide. Potassium's element number 19, it's a metal. Bromine is a Hunkelbrief twin. Now, bromine's a weird element. Room temperature, it's probably a liquid. Might be a solid, probably not a gas. Who knows what I wrote on this? It's not a gas. I'm going to put an L. K, for potassium, it's a solid. Bromine is a Hunkelbrief. And then potassium bromide, K is a positive 1 ion, bromine's a negative 1, KBr is the formula. It's ionic, so it's a solid. The Ks look good, right? 1K at the reactant, 1K in the product, but the bromines are no good. In order to balance this, I'm going to have to write and draw. There's 2 bromines in the reactant side. I can't put a little 2 in here because the formula is KBr. I have to put this 2. Right? That gives me now 2 bromines. See them? 2 bromines here. I got KBr, KBr. But that also gives me 2 Ks. How am I going to get 2 Ks? I have to put a 2 here also. Now, this is going to be in a 2 to 1 to 2 ratio. We don't write the 1 in front of bromine, Br2. Because we wrote Br2. That means there's 1. If there's more, we write a different number. We don't write 1s. So let's see what we got going on. Clear old drawings. And that's correct, except bromine should be a liquid. It's not going to be a gas unless it's really, really hot. And it's not really, really hot. 2 bromines in the Br2, 2 bromines in the product, KBr, KBr. And there's 2 Ks in the reactant, and there's 2 Ks in the product. This is balanced. All right, we're going to do 4 in a row really quick. Carbon and oxygen are going to make something called carbon monoxide. Now, if it said C plus O2 makes CO2, we'd be done. We're not making carbon monoxide. We're going to do the blue one first, carbon dioxide. There's 1 carbon in the front, 1 carbon in the product. So far, so good. I'm going to draw these all up, and we're going to do them, okay? 1 carbon, 1 carbon. 2 oxygens. How do I get 2 over here? I have to put a 2 here, and that gives me 2 oxygens here, and then now I have CO, CO. That's good, but I also have 2 carbons. That means I got to put a 2 in the front. So let's check. 2 carbons in the reactant, 2 carbons in the product, good. 2 oxygens in the reactant, 2 oxygens in the product, good. This is in a 2 to 1 to 2 ratio. This next one, copper and oxygen make copper Roman numeral 1 oxide. Well, let's see what we got going on. I got 1 copper here, I got 2 coppers there. I'm going to start out with a 2 here, but don't get too excited about that. All right, we're going to see what happens. Here, there's 2 oxygens. I only have 1 oxygen over here. In order to fix that, I got to double this. Now I have 2 oxygens on both sides, but look what I have. There's 4 coppers. This 2 has to come out, and I have to make this a 4. Now, does this balance now? 4 coppers in the reactant, 4 coppers in the product. 2 oxygens in the reactant, 2 oxygens in the product, 4 to 1 to 2 ratio. All right, next one up, the purple one, zinc. Zinc and oxygen makes zinc oxide. 1 zinc, 1 zinc. So far, so good. 2 oxygens, 1 oxygen. In order to get 2 oxygens, I'm going to have to double this up. 1 zinc, 2 zincs. That's no good. I have to put a 2 here. Now I got to start all over again. Remember what Glinda said? Always best to start at the beginning, and we're going to start over. 2 zincs in the reactant side, right here. 2 zincs in the product side, good. 2 oxygens in the reactant, and I have 2 O's. It's zinc oxide, ZNO, ZNO. 2 to 1 to 2. This next one, This is going to be a hard one. This is the last one of the day. This is the hardest one. Ready? Get ready to erase. I'm going to put a 2 here because I have to have 2 aluminums because there's 2 aluminums over here. But now look what I got. I have O2, and then on this side, it's O3. Now, what did I tell you about even and odds? The odd one is broken. The only way to fix it is to double it. So I'm going to erase my drawings, start over again. I had a 2 here, and now I have 2 oxygens and 3 oxygens. I got to double the odd one. So I have to put a 2 here, and that means I have to start all over. I'll go back to the beginning. There's 2 aluminums in the reactant. They're right here. And how many aluminums do I have in the product? 4. 2 and 4. I can't have a 2 here. I got to cross this out. This has to be a 4. 4 aluminums, 4 aluminums. That's good. Now I have 2 oxygens. How many oxygens do I have over here? I have 2 O3s. O3, O3, that's O6. 6 oxygens in the product. How am I going to get 6 oxygens over here? I got to put a 3 here. 4 to 3 to 2. So let's see what we got. I'm going to clear these drawings and we're going to go ahead. Ready? In the first one, 2 carbons and 1 oxygen molecule makes 2 carbon monoxides. That's balanced. In the next one, it takes 4 coppers to make 2 Cu2Os, and it takes double oxygen in the front because there's 2 oxygens in the product, also balanced. The zinc oxygen, it takes 2 zincs for 1 oxygen to make 2 zinc oxides. And in this last one, aluminum and oxygen makes aluminum oxides. It's in a 4 to 3 to 2 ratio. It's a lot to take in, but guess what? It's Thanksgiving. We have a lot to be thankful for. I'm glad to have my job, and I'm glad to be your teacher. Hopefully, you're glad to be my student, and you're glad to have the opportunity to learn chemistry. This is basic. It will get harder, right? But it's November. It's almost December. We're getting into the thick of things. We're balancing chemical equations. We're doing chemistry. This is basic knowledge. This is why we are making progress in the world. This is why people can fly into space. This is why we can fly airplanes. This is why we can make medicine. This is why we have a great life. This is why society is better, because we're intelligent and we're thinking and we're learning and we have this group mindset. We understand what we understand. It's not easy. But I'm good at this. And you're smart. That's why you're in my class. We'll get through this. Happy Thanksgiving. Goodbye. That's the bell. Perfect timing.
Thank your attention, please. We just had a few bus changes today. So if you typically ride Route 7, you'll be riding Route 8.
And I don't know how to turn this off. I'm having some trouble. There we go.